So for this video, we need to get a little up close and personal with the periodic table to kind of see the history with this. So let's take ourselves back in time to the early days of chemistry. We've got a group of chemists trying to figure out some way of doing something practical with the masses they have, their elements. So let's say you want to make something. Let's say you want to make carbon dioxide, and you got a lump of carbon, you got a lump of oxygen. And the only thing you know is your weight, but you don't know how many atoms you have. And you kind of need to know the ratio of atoms, so this way you can make sure you're making the correct amount of CO2, or you can at least predict how much CO2 you should be making. Well, this isn't an easy thing to do. You see, we've got these numbers on the periodic table. So we've got 10.8117 for boron, we've got 12.01078 for carbon, and really, this is how much an atom weighs on what are called atomic mass units, or AMUs. So one atom of carbon weighs 12.01078 AMUs. Well, we need to translate that into a gram, something we can measure in the lab. And what they found is that if we have 6.02 times 10 to the 23rd atoms of carbon, the atoms of carbon, that number of atoms of carbon will weigh that in grams. So 6.02 times 10 to the 23rd atoms of carbon weighs 12.01078 grams. Well, that's not really a practical number to work with. And the reason I say it isn't is if I add 1 times 10 to the 23rd plus 1 times 10 to the 21, you probably can't do it in your head, even though it's really easy. It's 1.01 times 10 to the 23rd. But if I ask you to add 1 and 0.01, you can do it really quickly. Reality is we just can't work with large powers of 10. It's not practical. So the mole was created as an intermediate unit. So a mole is 6.02 times 10 to the 23rd of something. So if we have a mole of carbon atoms, we have 6.02 times 10 to the 23rd atoms of carbon. Now the nice thing is, because it's that big, it means that every mole of carbon weighs that much. So we can work with ones, twos, threes, practical numbers. The other nice thing is that because it's a group of atoms, whatever is true for the individual atoms is going to be true for the mole. So let's say we're working with carbon and they all weigh 12 AMUs. Well, if we have a mole of carbon 12, then a mole of carbon 12 is going to weigh 12. It was true for the individual atoms, and it's going to be true for the moles as well. So this is the reason for working with the mole. It's an intermediate unit. It's meant to basically let us work with large numbers of atoms without having to carry the powers of 10s associated with them. It's going to act just like an atom or a molecule, but it's going to be much smaller and much more practical.